Welcome to this presentation where I'm going through the process of modernizing geometry drawing in our latest game, Alan Wake 2. My name is Tatu Aalto and I'm leading the graphics programming team at Remedy Entertainment. Remedy is a Finnish company and we have offices in Helsinki and in Stockholm, Sweden. We are currently roughly 380 people, and you might know us from games like Max Payne, Alan Wake, Quantum Break and Control. Today we will cover Alan Wake 2, which was released late 2023. In this talk, my intent is to guide you through the design process of updated geometry rendering pipeline we did for our latest game, Alan Wake 2. This talk is not about getting very technical or giving best practices. I'll start by giving a limited glance of rendering tech history at Remedy since original Alan Wake, which was released in 2010. This will hopefully give you a bit of perspective on where our focus has been and why we ended up doing the updates I'm about to present in more detail. After the history section, I'll go a bit into few details about art direction and then we move to more technical matters. Let's start with the history. Alan Wake 2 is a sequel, so it didn't magically appear from the vacuum. Original Alan Wake was released in 2010 and was largely built from scratch. Some code and tools from Remedy's previous game, Max Payne, were obviously used, but the world of Alan Wake was built with new and shiny editor, which was called World Editor. Alan Wake used proprietary terrain system that turned low poly ground into densely tessellated forest with adjustable biotype setups. Rendering was running on DX9 and used rasterization to additively blend each light on top of accumulation buffer, which was common setup back then. After Alan Wake, I joined and we started to work on Quantum Break. In Quantum Break, we put a lot of effort into improving lighting. Original Alan Wake shipped with almost fully dynamic lighting, but in Quantum Break, we invested into making a first version of our voxel-based global illumination system. In addition to global illumination, we moved real-time lighting to compute shaders, which meant packing the data into such form that all the lighting data could be accessed from single shader. The setup included packing all the shadows into atlases and moving per draw light parameters into larger buffers. Updated setup made it possible to handle more complex light transport setups and raised the limit of how many dynamic lights could be used. On geometry, we did few smaller changes, but the geometry rasterization remained very close to what we had in original Alan Wake. And then came Control, our lighting-heavy game that happens inside brutalist concrete building called Oldest House. For Control, the key element to making game look awesome was destruction and moody lighting. Geometry in Control was mostly very simple, but the geometry rendering that dated back to Alan Wake started anyway to hit limits on what it can do. We absolutely didn't have time to open the can of worms in order to redo geometry drawing. So we filled CPU cores with draw call building and concentrated to make materials and light play together as well as possible. This really paid off and we were able to pack Control with updated material system that was able to cater needs that materialized in form of ray tracing. Efficient ray tracing requires unified GPU access to all material and lighting data, and we had just that, plus redesigned voxel-based global illumination system that was many times faster than our original, which was shipped with Quantum Break. Then comes Alan Wake 2 and Art Direction. While Remedy has been growing over the years, we still consider ourselves a small and focused studio. We want to tailor our tech as well as possible to what we need. In terms of visuals, it means that rendering tech needs to align with art we do. The relationship isn't always simply dictated by visual desires. Sometimes technical possibilities can guide a way to a certain look. The most important bit is anyway to share a common target. For Alan Wake, there was a very clear target on art side. This slide is directly stolen from our art direction guide. Alan Wake 2 takes place in dense primordial forest. It's living creature itself, very dense, and the movement of vegetation has weight and physicality. We nominated our lead character artist to guide modeling effort of complex shapes of nature and used highly detailed scanned models as building blocks. The world of Alan Wake 2 isn't only dense, the world is also large. A lot bigger than any world we have done before at Remedy. Our target was to recreate massive scale of forest in Pacific Northwest. The scale of individual models is huge and the amount of detail to make the world feel rich and natural is very high. This is very different than the concrete indoors we did in Control. For the scale, one location that we were looking at was Crater Lake in Oregon, US. And in addition to real-world scale of the models, we wanted the world to feel big enough. Alan Wake 2 is not an open-world game where you can access everywhere. Still, we wanted vistas that can reach 4 to 5 kilometers from the player. This means that in total, our dense and vast world has a lot of geometry. And this leads us to technical vision. In this section, I will go through the bits that we lacked on the rendering side, bits that were preventing us from making Alan Wake 2 a game that we envisioned. This is probably pretty obvious after the previous sections. We had already struggled on getting draw calls built for our previous game Control, of which was happening indoors and was largely built from plain concrete. We had done all the easy optimizations, like instancing all the possible geometry and threading draw call building as much as possible. Some harder to achieve CPU side data shuffling would very likely make the engine run twice as fast as currently. Anyway, we knew that the limit on what can be pushed through the APIs was still relatively close. PCDX12 API just does not easily scale to very large draw call counts. In original Alan Wake, there was a custom system for drawing a lot of grass, but we had already deleted all of that. And also the whole terrain system that didn't really scale to modern needs. Even if we still had the tech from original Alan Wake, the movement of vegetation was not even close to what we wanted. Primordial forest was supposed to be a living creature of itself. We wanted the movement to be physically grounded and believable. And we wanted to have sensible authoring tools to define how the movement would be. Our old setups were done by moving individual vertices based on transformation hierarchy that was baked into a texture. There had been some DCC plugins to help with getting these vegetation setups working, but those had rotten way back in time. So at the beginning of Alan Wake 2, skinning was basically our only nicely working geometry deformation pipeline. We had done a lot of destruction with normal linear bone-based skinning in control, but saw that pipeline to start hitting limits on how much memory can be moved around between CPU threads and eventually to GPU. Regardless of technique, we were lacking ways to push better parametrizations to content side, and it also accounted materials. At some point, our material format had degenerated to something that was almost beyond patching. The essence of any engine-side data modification is to be able to patch old content to a new format without breaking any existing work. Now, we face the fact that for Alan Wake 2, we had to rewrite at least our material blending in order to be able to create good-looking terrain for the world. Old terrain editor was based on geometry modeling in engine and using vertex colors as material blend weights. We wanted to simplify authoring and use texture painting painted height fields, as there wasn't true need for caves or other complex shapes. This required heavy changes to what our material data was. Completely separate need of splitting the game-specific shaders out from the engine started to lead us towards new material setup that becomes our first technical vision to go through in high level. So in order to keep the individual materials easy to understand, we wanted a single location that can define data and logic related to it. Our game engine is C++, and the editor used for authoring materials is C#. We have previously supported C++ side logic for patching, but that had a lot of workflow niggles when integrated to C#. In order to find a middle ground and avoid very complex pure data-based logic setups, we felt that using scripting language is lightweight and easily extendable solution. We think that the most sensible pure data setup would have been to expose materials to node graphs, but that has never been a popular option at Remedy. We like to keep graphs on higher level and write code where the low level logic is needed. Full rewrite of the material data handling required us to patch all the material types. Fortunately, we had kept our material definitions always very simple and very few in numbers. Even bigger changes were needed for geometry drawing. The longer-term goal in regards of geometry had been forming up for quite a while during development of our previous titles. It was obvious that in near term, the graphics APIs will not provide a huge leap in terms of how many draw calls can be submitted from CPU to GPU. Similar to what was done already previously with lighting and materials, we wanted to move geometry handling to GPU side also. Relatively early in development of Alan Wake 2, we decided to drop the support for previous generation consoles. Focusing to single console generation opened up a perfect spot for doing a full sweep on drawing meshes. Moving to GPU dispatched rendering would also mean drastic improvement to occlusion culling. We had been using CPU-based culling since the original Alan Wake, and that pipeline just did not work with alpha testing or deforming geometry. So the GPU-driven approach felt like a very good match for dense primordial forests. Ray tracing setup we didn't want to change from control. We would still use matching geometry on ray tracing and rasterization. The reasoning is that we don't want to lose the lighting precision gained by accurate global geometry access by ray tracing. This means that all the deformed vertices need to be written into memory for BVH building. The current state of ray tracing APIs also means that the only practical way to match geometry is to use discrete LODs. We also didn't want to redo LOD pipelines for this game, as it didn't seem absolutely necessary. Last but not least, we have deformation of geometry. As previously said, we wanted the forest in Alan Wake to feel physical and grounded. The best way to approach this kind of setups is to do proper deformation hierarchy and simulate the movement with some physics model. As also said, the only nicely working bit in our geometry pipeline was the skinning that we had fully moved to GPU during quantum break in order to do huge simulated set pieces that could be animated back and forth in time. During control, we had already also done a compute shader setup that calculated skinning and wrote the deformed vertices to memory so that they could be fed to ray tracing BVH builder. Since we also had a plan to extend material system to be more flexible, it was pretty easy decision to expose APIs for manipulating bone and vertex data arrays and let VFX team go crazy with it. We had absolutely no experience on how this would run, and there wasn't really time to do a proper feasibility study on performance, so we preemptively told modeling teams to target less than a million active bones. The ballpark came from comparing the load to amount of pixels in some common render targets. I think this was actually pretty much the only content budget that we didn't end up going over during the development. Since I don't have time to cover everything in this presentation, I forward you to watch the in-depth talk from Kia that was presented in GDC. And now let's move on to actual design and start with geometry. We were already relatively far in production when we finally got into implementing most of the technical vision, which is good and bad at the same time. Our guiding principle has been that even with large changes, we want to keep the engine running and be able to validate what we do against real data. Sometimes not completely possible, but with geometry we definitely didn't want to break compatibility. Geometry materials and textures are our most reused asset types, and it's critical to be able to move these flexibly between projects. So in order to make tech that fits into existing content pipelines, we need to start the design by looking at what kind of data do we have and how could it be represented with indirect rendering. Intention is to sketch out required high-level setup before diving onto GPU algorithms and optimization. As said, we had a bit earlier dropped out plans to support previous generation consoles. This puts us into pretty clear position on what is the API that we need to deal with. Central limitation with the current APIs is that most of the pipeline state needs to be changed from the CPU. So when changing, for instance, shader or blending mode, we need to split GPU processing and do CPU side setups in between. This means we need to figure out what is the piece of geometry that can be always drawn within a single GPU execution. For us, this is cluster of triangles that belongs into a single detail level and has single material and transformation attached to it. This is one-to-one mapping for existing raw calls when not using instancing. We store these combinations of geometry, material, and transformation in Mesh engine. Each stored cluster has 32-bit persistent handle that can be used on CPU and GPU to access all the relevant data that's connected to cluster. On the left side, you can see what makes up the cluster data. Our geometry streaming is implemented to work by creating separate buffer per mesh. We wanted to start by using the existing setup and didn't start to gather vertex and index data into global large buffer. This setup meant that all the geometry buffers are behind bindless access on GPU and the indexing works directly with cluster handle. While the bindless setup does add overhead to buffer access, we had pretty good experiences about how it will perform based on ray tracing implementation of control. If the access performance was to become problematic, the plan B was to transition to large buffers later. In addition to simplicity, we were mentally okay to rather take a small hit with access cost rather than needing to deal with residency issues on PC when running low on memory. On the right, we are approaching Coffee World, which is amusement park in the game. In this location, we have 225k clusters of geometry streamed in. The amount includes separate clusters for each discrete detail level, and the amount of detail levels is up to 8 per mesh. Next step is to take a set of clusters and draw them in certain rendering passes. We draw geometry into many passes of various sizes. The passes that contain most clusters are going to be drawing depth and geometry buffer for camera and filling shadows. We also have a lot of passes where only a small set of clusters will need to get drawn. In practice, none of the passes will ever contain everything that was registered into the mesh engine. Some of the passes will also be collected dynamically based on gameplay and effect scripts. It's important to notice that some of the passes share visibility for a certain cluster, but might have different splits for changing the pipeline state. So in other words, for a set of clusters, we want to define multiple passes that are organized individually into drawing buckets that share the pipeline state. Our cluster set holds a configuration for a number of passes that contain the same group of clusters. Each cluster inserted into the set will have a bucket index for each pass in a set. So if the set contains 2 passes that are depth and geometry, each inserted cluster will have 2 bucket indices. Cluster set is now something that we could already use for drawing geometry. We built our first prototype for indirect drawing on top of this data. Some numbers from the location I talked earlier already. Out of the total amount of 225 clusters, almost 200k are inserted into opaque pass. And out of these 200k, only 40,000 are active. Active here means that the cluster is part of discrete detail level which is currently in use and the cluster has not been temporarily hidden. On the right hand side debug window, you can also see that we have 16 different sets created in this location, and also that the opaque set contains 3 different passes: depth, geometry buffer, and visibility. Before we dive deeper into the implementation, let's add in the container that we use for storing visibility. Since the set is just a collection of geometry, we sometimes want to resolve visibility for the same set of geometry from multiple viewports. Rendering into shadow map is a good example of this. The visibility is a separate container that is always associated with one set of clusters. As discussed before, we designed a set to share visibility of an cluster between multiple passes. This means that the visibility container will have a single Boolean state for all the clusters in a set. Or in other words, visibility is a bit per cluster, and that bit is shared for all the passes in a set. Remember also that the passes in set can contain different amount of pipeline state changes that are needed for rendering. The typical case with pre-depth and geometry buffer, for example, is that many geometry buffer shaders share the same depth rendering. So in addition to visibility, we want a compact list of visible clusters per bucket in each pass. For this, we reserve storage for 32-bit cluster index for each visible cluster for each pass. This is our high-level setup. We have a global mesh engine that contains all the streamed-in mesh clusters. Each cluster can always be drawn with single pipeline state. Then we have groups of clusters that are mapped to be drawn in certain passes. And finally, we have visibility of a set for some certain viewport in a scene. On the location that I've been referring, we have around 5,000 visible clusters in opaque set. One problematic case remains that doesn't fit into this model. As the whole GPU-driven design is based on grouping the draw calls based on pipeline state, passes that use depth-based sorting are going to be problematic. We have previously kept opaque geometry roughly ordered from front to back in order to take advantage of overdraw elimination with depth testing. It's still possible to sort draws within each pipeline state, but the resulting global order will be heavily influenced by the order in which the states are drawn. Transparency is even more problematic, as the incorrect draw order will not only decrease performance, but also causes visual corruption. But let's worry about this later. Next we will look at how to configure this pipeline with something that can be drawn. Shaders. In this section, I will briefly go through how the scriptable shader pipeline used for redesigned material data turned out looking. I will also show how we use it in GPU-driven geometry drawing. As mentioned, we want to collect all the shader-related data definitions, metadata, and scripted logic into the single location. In this case though, the single location is two files, as having HLSL and Lua code in the same file would make the text editors work wonky. So we have one file for shader code, another file for Lua scripts. These files must have same name and they are in same folder to make them easy to find. Shader code file is pure HLSL, so I won't cover that, but I'll show how the shader Lua script looks and how it's used with geometry rendering. First comes the material declaration. We tag all the shaders with usage, which in the case of snippet on the right side is material. The data version of the material is 20, so this script file contains patching over 20 versions of data. On the right side script, you can also see that the material exposes diffuse albedo map and multiplier for user to edit. Both C++ and C# code request these definitions by calling the Lua functions, function called properties. Lua script also contains the grouping of shaders to techniques and exposes few additional parameters that can be used to parametricize compiler or certain pipelines. We target to keep the amount of shaders low. For GPU-driven geometry pipeline, we use Lua scripting to define previously discussed buckets for named passes. The script you see on the right side is feeding all the possible pipeline states that are needed to draw this material in engine. So in this specific case, the pass called depth will be set to contain two different pipeline states that we call buckets. First state uses counterclockwise triangle culling without any flags. The second one is specialized for double-sided alpha-tested geometry. The pass initialization is called once when the cluster set is constructed, and after that the setup is considered static. Instead of reconfiguring existing cluster sets, we create new ones for specific use cases and keep the widely used engine-defined passes untouched to avoid expensive data shuffling. Once we have passes set up, it's time to insert clusters into correct bucket in each pass. In order to assign geometry cluster into a bucket in pass, we again run Lua script. This time we read geometry and material properties of an cluster and determine again what kind of pipeline state is needed for drawing. If the requested pipeline state doesn't match to anything that was earlier registered, we raise an error as the setup is invalid and the cluster cannot be drawn. It's time to dive deeper. We know how to set up the pipeline states for rendering passes and how to map cluster to be drawn in one of them. The data is packed into compact representation and everything is organized conceptually into chunks that need to be drawn. What follows is going to be the most technical part of the presentation. To visualize what the cluster set, pass and bucket means, I have here two concrete setups to look at. Note that the setups seen here are simplification. In reality, we have a bit more complex configurations. Looking at the top one, you can see that the name of the set is opaque. This set is targeted to be used for filling pre-depth and later geometry buffer. The depth pass is split into two different buckets. Bucket 1 contains all the geometry clusters that used alpha testing, and the bucket number 2 contains the clusters that don't. Every cluster that contributes to opaque rendering is going to belong to either one of these. Geometry buffer filling is a bit more complex as it has 3 buckets: here, eye, and standard. Every cluster that contributes to opaque rendering is also going to belong into one of these 3 buckets. So you can have hair material that is either alpha tested or not, and so on. The below example is even more simple. Emission cluster set is only used by materials that are emissive, and there is only 2 buckets to choose from. We have one global engine that contains all the streamed in mesh clusters which can be drawn. The numbers next to the engine are handles for each cluster and can be used to modify cluster-related data between frames or to remove cluster from rendering. The cluster handles in engine are persistent and can be used to directly access data arrays on GPU, so we reuse handle indices over time and track which handles are currently active. In reality, there obviously isn't a list of numbers stored in engine, but an array of booleans for activity and various other data that's needed for drawing. Cluster set is a collection of global mesh cluster handles that are drawn to specific passes. So the set is compacted pile of geometry that contributes, for example, to opaque or transparent rendering. This data is stored on CPU, and this time we do have actual 32-bit integers stored in memory. Most of the cluster sets contain only a small subset of all the handles. Visibility is resolved on GPU and contains again a subset of cluster handles. Since the set can define multiple passes that have own subdivision of draw calls with separate pipeline states, we further process the visibility to draw buckets. So we need to combine these 2 diagrams in order to have each geometry cluster to get rendered with correct pipeline setup. So the per pass setup looks like this. We have 5 passes where 2 first ones are drawn into depth buffer. 3 last ones write out geometry buffer. Based on visibility, we can now put geometry clusters into correct draw buckets. As shown earlier, each geometry cluster has Lua setup that declares in which bucket it needs to be drawn. The lines in diagram are marking where the visible clusters are stored. In order to make it possible to do occlusion culling based on previous frame visibility, we store the current visibility as a bit mask. So the green clusters are visible and the red ones are not. Here you can note that the cluster handle 3 was not visible on previous frame. In addition to current visibility, we collect geometry that was not visible previously but has become visible on the current frame. Handle 3 gets marked as newly visible on the row previously called. Then, as a last step, we update visibility of each cluster in a set. Visible and previously called rows will next get translated into indirect commands. For the vertex shader based drawing, we need 3 buffers. Count buffer is the simplest one and will just contain amount of draws in each bucket. Visible buffer contains draw calls for all the clusters that are visible, and it's used on passes that need to be filled from scratch. For the passes that have already been initialized by drawing previous frame visibility based occluders, we only need to draw geometry that became visible on the current frame. These draw calls are written into previously called buffer. There is more detailed presentation about similar occlusion culling, for example in GPU-driven rendering pipelines, which was presented in SIGGRAPH 2015. Why would you stop at vertex shaders? We wanted to avoid added overlap that is caused by not being able to sort geometry by depth. In terms of performance, it's essential to run culling on small enough granularity. Most of the platforms that Alan Wake 2 runs do have support for mesh shaders, so we decided to try meshlets while on it. Meshlet-based rendering shares most of the framework I discussed earlier, as you would expect. In addition to streaming in vertex and index data for the mesh, we also stream in Meshlet header arrays if the target hardware supports mesh shaders. If you don't know what a meshlet is, you can think it as a small group of triangles. In our case, the meshlet can contain up to 64 triangles. Our main motivation with the meshlet rendering is to achieve more accurate culling. We add a step that does per meshlet culling and will modify all the material shaders to work with both vertex and meshlet shaders to avoid code duplication. We started the meshlet implementation by writing a simple mesh shader to figure out the exact data that is needed for the culling pass from the culling pass. After finding and reporting a lot of driver crashes, we ended up to a solution where we do single indirect dispatch mesh per pipeline state. For this setup to work, we need handle to mesh instance and index of meshlet that we are drawing. We needed to slightly modify the culling that was presented earlier and decided to split the functionality into 2 passes. The first pass is dedicated to output indices of visible clusters in a set and is essentially the same as presented before, but with simplified output. With meshlets, we don't track visibility of individual clusters. The clusters are just written out as plain handles. This pass is implemented as a compute shader where each thread is handling single cluster. The second culling pass is reading the previously computed visible clusters and does visibility culling for each meshlet. This is also an compute shader pass where each group is handling single visible cluster and each thread in the group computes visibility for a single meshlet. As said, the output from this pass is a buffer that contains two 32-bit handles that are consumed by mesh shader. The data output can eat a lot of memory if you allocate space for all the streamed in meshlets. We ended up using async readback from GPU to figure out practical limits for storage. Lastly, in order to avoid duplication of the shader code for vertex and meshlet shading, we ended up to using very simple macro-based shader entry point generation. We have a lot more details about meshlet rendering and performance numbers presented by REAC in Digital Dragon's presentation that's linked here. And next, we get back to figuring out what to do with transparency. As we discussed earlier, it's not possible to order the draw calls based on depth, and incorrect draw order will result in broken alpha blending. Let's start again by figuring out what do we need to support. We use multiple different techniques to fill in transparency, and the end result is a combination of everything. In general, being able to work on many techniques has made it possible to find pretty nice balance between performance and visual fidelity on our previous games. We originally introduced multi-resolution transparent rendering in order to cut fill rate to close by effects. In practice, VFX very quickly moved to use the low resolution targets to fill low frequency effects like smoke and fog efficiently. We wanted to keep multi-resolution setup but address the ordering issues that filling to different targets had caused. In our previous setup, only the voxel density has been correctly blended against different resolution targets. Mega shader is the first obvious candidate. It's relatively easy to get running with and would only need GPU sorting. Merging traditional geometry and particles would be a mess, but most likely doable. Bigger headache would be to somehow merge content-side custom effects to the same framework. Mega shader felt very inflexible and wouldn't solve issues with blending multi-resolution targets together. Ray tracing is other relatively straightforward method that can solve transparent sorting on GPU. Unfortunately, it has similar issues as Mega shader, since you will need to be able to handle all the effects inside single traversal kernel. This one we did think a bit more, as the framework on ray tracing is a bit more flexible with having a lot of shaders. Ultimately, we were worried about performance and the support on non-ray tracing hardware. So in the end, we decided to go with order-independent transparency. Weighted blended order-independent transparency is a nice and very cheap method, but we've tried it before and determined that the quality wasn't good enough for what we needed. Main issue with this technique was the inconsistency of how the surfaces with different opacities were looking. Stochastic was ruled out without creating a prototype, as we were afraid of the issues with noise. Alan Wake has pretty wide intensity range due to realistic lighting, building filtering that nicely handles effect sparks, and for example car window under sunlight seemed like a bit too big of a gamble. Fortunately, moment-based order-independent transparency looked very promising and turned out to be pretty easy to test out with the prototypes. moment-based order-independent transparency, MBOIT, is two-pass method where you first rasterize all your geometry in order to produce depth-based transmittance. On the second pass, all the geometry is filled again into a color target with additive blending, but this time by reading the transmittance from the buffers that were earlier filled. Supporting correct transmittance with multi-resolution rendering means that we first fill each transparent core to some single transmittance target and then combine all the resolutions together. After combining pass, all the resolutions must contain transmittance from all the geometry. As said, we also support volumetric density that can be mixed together with transparency. This is a great method for filling low-frequency fog and smoke effects with low fill and light evaluation cost. Combining opaque, transparent, and volume needed a bit of tweaking, but provided seamless result in the end. Similar to many others, we pre-process volume density into volume that contains in-scatter and transmittance based on depth. So the data content by the volume is really similar to what MBOIT operates on. We didn't figure out a neat way to translate volume transmittance directly into moment-based transmittance. Instead, we opted to instrument transparent color fill shaders to evaluate volume and MBOIT transmittance separately. This was the simplest possible solution to us, as we already had volume transmittance accounted in transparent shading. Other way round, we combine volume scatter on top of opaque geometry in very end of the pipeline. So at that location, we now evaluate also the moment-based transmittance in addition to volume transmittance. With the setup presented here, we were able to nail the visual look of Alan Wake 2 from the geometry rendering side. The world is filled with rich geometry, vegetation movement is grounded, and the different methods of filling transparency work together seamlessly. Moving raw dispatches to GPU allowed us to delete old CPU-side threading code, and the bottleneck is now on GPU and in streaming. Finally, I would like to thank our art director Janne Pulkkinen, from whom I stole a couple of slides for this presentation, and the whole programming team that was contributing for the tech presented here. Let's end with a short video of how this all looks.
Peggy 18.
I hope you enjoyed this presentation. Certainly, I had a lot of learnings from this. Tatu is a lead graphics programmer at Remedy Entertainment, as he mentioned at the start of his conference. He's actually been working in the games industry since 2003 and has a background, as you can clearly see, in real-time graphics and software rasterization before that. He spent most of his industry career on building rendering technology, and he's given talks about computer graphics in various conferences on games and real-time rendering. So let's welcome him for live questions. Tatu, if you can join me now. One second as we bring him back. Aha. And now we're welcoming Tatu here in live Q&A session all the way from Finland. Thank you, Tatu, for making here.
Thank you.
Heaps of questions from our audience in Discord who are super eager to learn more. So I'll start with a question from Steve Karalevich. Can you elaborate on the 14 materials used in control? Is it material types or actual unique shaders? How did you accomplish this? Did you rely on UBI shader approach with a set of dynamic switches? Did it include vertex deformation variants? By the way, this was eagerly aided by a number of other attendees eager to learn about this.
Yeah, sorry, I was maybe slightly hazy about it. It's material types, not individual material instances. So yeah, this is 13 material types. We actually have a lot less in Alan Wake. Alan Wake is maybe 5 or 6 or so. So it's basically standard material layered one, hair, iron. That's about it, I guess. So this is basically, yeah, they're actually relatively compact. They are pretty basic
Awesome.
ones, but it doesn't include kind of like particle and effects and that kind of stuff. Obviously, there's more shaders. I think I had in slide, I have maybe 2,500 shaders total in Alan Wake.
Awesome. Great clarification. Thank you. Next question is from Khalil H. Newer. By matching geometry and ray tracing and rasterization, completely one-to-one, including the same LOD and effects and decals, was that what you meant?
Not effects and decals, only matter. We have this specific mesh decal concept, which is not like projected quads. Those are included, but not effects. So basically opaque, transparent geometry.
Next question is from Alper Askan. Do the clusters end up helping in any way with the hierarchy building with ray tracing?
So the clusters are basically draw primitives in this case. So it's not clusters as like Meshlet. So we do feed clusters into the BVH building directly. So they help in that sense, but that's kind of like the basic block that you put into BVH.
Gotcha. Another question from Sam Willis. Did you have any issues with pop-in false negatives using calling data from the previous frame? And if so, how did you handle them?
No, this method, I do suggest to check the Seb's presentation from 2015 advanced. So it's basically, you don't draw a reuse depth buffer as from the previous frame, or you don't reuse anything that was actually drawn. You only reuse the visibility of previous frame, but draw everything with the current frames transforms, so it doesn't lead into popping.
Got it. Question from Martin Calhoun. How many indirect draw calls are you issuing now as compared to those 2K draw calls mentioned in case of control?
What would I lie? I mean, we have maybe less than 10 depth shaders. So depth pre-pass, which we do before geometry buffers. So it's like less than 10 geometry buffers. 10.
This was the moment for you to bring out the palms. Like, this many.
Yeah. Yeah. It's not very many. But there's of course more draw calls, and I mean we have some older setups for particles and that kind of stuff, so they do add some amount of draw calls, but it's a lot smaller amount than we had before.
Question from Scott Hoffman from Monolith. Do you perform a separate calling pass for ray trace geometry to widen the set of geometry that can affect visible geo?
No, we have everything in BVH. There's no
separate culling for that stuff. It's used for indirect and for shadows, and shadows are obviously beyond camera and so on. In control, we did use expanded view frustum, but that worked out because we shot relatively short reflection and diffuse rays, so you couldn't get very far from the camera viewport. But with the shadows, it becomes problematic. Obviously, we use shadows from all the lights. So,
gotcha. Next question is from UC Nutila. How large are your clusters in terms of triangle counts? Are they fixed size or variable size?
yeah, the clusters are kind of like normal draw primitives, so they are basically coming directly from the modeling side. So depends on, they are variable sized. Then there's meshlets, which are 64 triangles per meshlet, but they're different concepts.
Next question from Daniel Olson. What benefit did the Lua shader companion script have? It felt somewhat like it's doing a roll of material. Is that how you approached it?
Well, it's kind of like logic related to shader, and it's not only materials which are actually using the Lua setups. So we have all the shaders using the same Lua setup. So there's all kind of scripts. For instance, since we have separated materials and deformation of geometry, for instance, we backbone data from the Lua side directly, and the normal materials are also constructing, or that they are basically on content side, and they can actually do indexing for the textures into the pointless arrays, and then back actual data buffers directly from the Lua.
Nice. Next question from Santeri Salmiarvi. Did you experiment with amplification shaders for Meshlet calling in addition to the compute implementation? And there was an add-on to that from Scott Anderson. Is there a reason you didn't use task amplification shaders outside of certain platforms, maybe not supporting them?
We tried quickly at some point, but ended up not needing to add a lot of geometry. We have a height-based terrain system, or ground system, whatever you call it. So the height field is obviously dynamically tessellated, but it's not using amplification shader really. So the answer is no, we didn't use it. We tried, but not used it.
Tian Ning is asking, how did you hide GPU to CPU readback latency?
We actually didn't. This was probably maybe related to the optimization of memory footprint. So basically we read back the amount of meshlets drawn on previous frame, but then we multiply the amount of meshlets by maybe 2 or something like that, and then that was just enough basically to fit the next frame always. But yeah, it's possible to end up in the situation where you have 5 meshlets first, and then the second frame has million meshlets, and then at that point you will obviously run out of the budget, and then you will not have all the meshlets on the screen. But this was actually not a practical problem for us.
Gotcha. David Nadasky is asking, does your OIT implementation require rasterizer order views hardware feature?
No. There is the MBOIT code, which is available on GitHub maybe. I can't remember where, but anyway, it has a path which does require, which improves accuracy, but no, we didn't use that one.
Gotcha. And somewhat related to the OIT, Adrian de Tuquil asking, are you using 32-bit targets for your OIT implementation, and did you experience floating point precision issues with large depth differences between transparents?
God damn, I need to confess that I can't actually remember, did we end up with 16-bit or 32-bit?
This is a perfect opportunity to
tried
look at your
both.
code and later
Yes.
later answer it in Discord. That's cool.
Yes, exactly. I can come back to it. I think we use 4 movements at least.
Super. Francesco Ciafarello Stiardi is asking, he actually complimented you, saying great talk, but also you mentioned the fully matching rasterization and ray tracing geometry with vast amount of vegetation in the game. Does that include all the alpha tested geometry? If so, are they processed with any hit shaders or in an alternative way?
Yes, that includes everything. They are as is. The material model that we have is constructed so that the alpha testing is always same for any material type. So we basically have one any hit shader which actually handles all the alpha testing or materials. So it's relatively cheap, but I mean, yes, there is a lot of alpha tested stuff. So it's relatively, I mean, it does become expensive. Was there many parts of the question? Sorry.
There are a few other questions in Discord. We'll tag we're at times. So
I can get back to them.
Yeah, you can get back to folks on Discord at your, whenever it's possible for you. But let's thank the speaker for an amazing presentation and really transparent and earnest answers to the Q&A. Thank you so much, Tatu.
Thank you.
And now we'll go to a break and we. Oh, sorry. Go ahead.
No worries. Thank you for organizing.
Pleasure.
Nice conference.
And
awesome.
We'll go to a break, and then we will have a talk by Simon Ashbark at 9:30 a.m. Pacific Standard Time. So come back for our next talk on optimization for UI rendering. Thank you.